Okay, in this video what we're going to do is we're going to look at how do you construct a Taylor polynomial from scratch. In the previous video we looked at conceptually what it is. We looked at several different graphs and showed you how you can construct a polynomial, at least in theory, to make it fit almost any curve imaginable. So let's review that real quickly. And the red is e to the x and my blue is my polynomial. Now this particular polynomial is a 0-degree polynomial. It is basically the graph f of x equals 1. And all I've said is I want the function value of e to the x and the function value of my polynomial to be the same when x is 0. And you can see they're both 1. Okay, well what if I went a step further and I said let both of their first derivatives be the same at x equals 0. Okay, so now we can see that both e to the x and the blue line, which is tangent, looks like they have the same slope at x equals 0. And you can see that this line actually does a better job of approximating e to the x, at least as long as we're really, really close to 0. Well, then we said, what if their second derivatives are exactly the same when x is 0? Well, what's the second derivative tell us? The second derivative of a function tells us the concavity of the function. And you can see that at 0, both of these functions are concave up. And you can see that my blue polynomial is taking up more and more of the red e to the x function. Okay, well I can continue this. I could say let their third derivatives be the same, let their fourth derivatives be the same, and finally their fifth derivatives be the same. So this is an example of a fifth-degree polynomial. This fifth-degree polynomial actually does a pretty good job of approximating e to the x, at least in between -2 and 2. So if I wanted to know what is the value of e to the 1/2, or the square root of e, this fifth-degree polynomial would actually do a pretty good job. So how do you go about computing a Taylor polynomial? So right here I have my function e to the x, and I have this random polynomial function that maybe you know where it came from, maybe you don't. But first, let's just go ahead and talk some notation. The p stands for polynomial. The 5, the subscript 5, stands for fifth degree. So this is a fifth degree polynomial of x, and this is what it equals. Okay, and to show you that this really is the thing we were just looking at, let's just go back to that graph and notice that my n is equal to 5. Okay, and down here I have a table of values. These dots that just popped up are the actual function values at 0, 0.5, 1, 2, 3, 4, and 5. So if I was interested, what is e to the 1/2? E to the 1/2 is right here. Okay. Now, if I say go ahead and plug 1/2 into my polynomial, let's see where that lands. And it looks like it landed right on top of e to the 0.5. So if I go to my table, in fact, and look at the values, the actual e to the 0.5 is right here, 1.648, and my approximation from my polynomial is 1.648. So a fifth degree polynomial looks or appears to be good enough to evaluate the square root of e, at least if we wanted to be accurate to 3 decimals. Okay, but you can notice right here at 2, e to the 2, the actual e to the 2, I don't know if you can see that, but is a little bit higher than my polynomial value. And then here at e to the 3, it looks like my approximation is off even more. We can go to these values and see that e to the 3 is really 20.08, and my polynomial evaluated at 3 is 18.4. So how do I build that polynomial? Well, at this point, I'm not going to derive this. I derive this in another video. If you're interested in that, you can go watch that. But for right now, I'm going to give you this, and this little formula, if you will, is going to be our tool to construct a polynomial for any function that's centered at 0. Okay, so the f refers to the function you're trying to approximate. 0 is going to be the center that is going to be the center of our polynomial. And it turns out you can shift this center around. I will get to that later, probably not in this video, but another one. And then this is obviously f prime, f double prime, and this is not f cubed here. This is the third derivative of f evaluated at 0. And we could do this indefinitely. We can go out and take up to 50 derivatives if we want. You know, the nth derivative evaluated at 0 multiplied by x to whatever you chose n to be divided by n factorial. That's our sort of formula to compute a Taylor polynomial. So let's see how we got this guy right here. Okay, well, what is f of 0? What is e to the 0? And anything to the 0, with the exception of 0, is 1. Okay, so what's f prime of 0? Well, the nice thing about this polynomial is every derivative of e to the x, the first derivative, the second derivative, the third derivative, they're all going to be e to the x, which is an amazing fact in and of itself. But f prime of 0 is also going to be 1 multiplied by x. F double prime of 0 is 1 multiplied by x squared divided by 2 factorial, which is just 2. And then the third derivative is 1 multiplied by x cubed over 3 factorial, which is 6. We'll do 2 more here. Fourth derivative evaluated at 0 is 1 times x to the fourth over 4 factorial. 4 factorial is 24. And the last one is going to be the fifth derivative evaluated at 0, which is still 1, times x to the fifth over 5 factorial. But 5 factorial is really 1 over 20. So this green polynomial here, we could clean this up a little bit. We can, you know, well, I guess that is pretty cleaned up, but we could get rid of all the ones if you wanted to, and it would kind of look like this up here. But that green polynomial really is the function right here. Okay, so you can't see all the terms there, but I'll just scroll through them real quick just so that you can be sure that it really is the polynomial of fifth degree. So you can see there's my fifth degree term right there, and you can see that fifth degree polynomial does a pretty good job of approximating e to the x, at least as long as we're centered around 0 pretty closely. Well, to get even more accurate, you can increase the degree of your polynomial. So I can actually take this up as high as I want, and the more terms I add, the more accurate my polynomial is going to be. Now you can see that at least in this window, my polynomial and e to the x are virtually indistinguishable. Okay, if I zoom out a little bit more, you could see that right out here around, looks like -11, my polynomial starts to kind of do its own thing. But I can go even further, and you can see that this polynomial just continues to lay down indefinitely on e to the x. E to the x is going to continue to go out this way, and if I added enough terms, this guy would lay down on all of e to the x. Okay, what about a different function? What about sine of x? What if we wanted to come up with a polynomial that does a good job of approximating the sine of x? So the first thing you'll notice is I have my function here, and then I've just written out the basic standard Taylor polynomial for any function. So one thing you're going to notice you're going to need is you're going to need to know derivatives. You're going to need to know the first derivative of sine, the second derivative of sine, third, so on and so forth. So let's build a fourth degree Taylor polynomial for sine, a fourth degree. And before I do that, let's just go ahead and look at the derivatives for the sine. First derivative is cosine, second derivative is negative sine, so on and so forth. And then you can see that once we get to the fourth derivative of sine, we start to repeat. So this is our pattern right here. Okay, the second thing you'll notice we're going to need to do is we're going to need to evaluate all of these derivatives at 0. So I've gone ahead and done that for you, and there they are. So cosine of 0 is 1, sine of 0 is 0, Cosine of 0 is cosine of 0 is 1, but it's negative, so it's negative 1. And finally, the fourth derivative evaluated at 0 is 0. So let's just go ahead and fit this pattern. What is f of 0? Sine of 0 is 0. Plus the first derivative evaluated at 0 is 1. The second derivative of 0 right here, second derivative evaluated at 0 is 0. So plus 0 x squared over 2 factorial. You can see that that's going to wipe that term out. Now, the third term is going to be the third derivative evaluated at 0, which is negative 1. So plus negative 1 times x cubed over 3 factorial. And then finally, the fourth derivative evaluated at 0 is 0. So you can see that that fourth degree term is going to get wiped out as well. Now, a couple of things I want to point your attention to here. One, I started this off by saying let's go ahead and make a fourth degree Taylor polynomial. And you'll see that the fourth degree Taylor polynomial, let me move this up a little bit, whoops. The fourth degree Taylor polynomial is going to be the same as the third degree Taylor polynomial. X, this term gets wiped out. This is really negative x cubed over 3 factorial, and then your fourth degree term gets wiped out. So this is both the fourth degree polynomial and the third degree. I'm just going to call it the third degree polynomial. Just, I don't know, so that all the threes live happily together. I don't want to confuse you if I put a fourth there. But this is a third degree polynomial and a fourth degree polynomial that should be approximately sine of x as long as we're close to the center of 0. Okay, so let's go take a look at the graph of these things real quickly. So the red curve you should recognize as a sine curve. So here's 0, here's 2 pi. You could see one cycle of pi. And then the blue represents my third degree polynomial, which you can see looks pretty close to the sine curve as long as we're in between right around 1.5 radians and negative 1.5 radians. And then if we came over here to our table, and I wanted to approximate, well, let's just use this one. If I wanted to know what is the sine of a half a radian, this is what the sine of a half radian should be, and this is what my Taylor polynomial tells me that it is approximately. And again, as long as your exactness is only 3 decimal places, this very simple third degree approximation will suffice. So there's a brief introduction on how to build a Taylor polynomial. In the next couple of videos, we'll be doing more examples of these along with shifting the center off of 0. We'll see you then.